Hi, everybody. Today we have the second seminar by Francisco Tello Ortiz. Francisco from Chile. He's from the University of Antofagasta in Chile. Francisco has a lot of experience working on general relativity and beyond general relativity, and today he's going to talk about hairy black holes and wormholes space-times by MGD. So Francisco, whenever you want, you can start, please.
Okay, thank you very much, Jorge, and to the audience to stay here today. Okay, today I'm going to present a work, okay, hairy black holes and wormhole space-time by the MGD. This work is in collaboration with some people, Professor Andrea Alvarez, Angel Rincon, and Saibal Rai. So the motivation behind this research lies on three main points. The first one is that general relativity predicts simple solution for black holes space-time. As we know, general relativity is one of the great scientific achievements of last century, with hundreds of observational corroboration. Then it is clear that this theory allows us to investigate, to understand in a natural framework this kind of objects. The second main point is black holes are ideal to study gravitational field in a strong regime. And the third one, and the most important one, is the Norher theorem. As we know, the theorem established that black hole solution should not carry any other charge than its mass, the electric charge, and the angular momentum. Then in this table, you can see a summary, okay, regarding this theorem. Here we have the most commonly known black hole solutions in the concept of general relativity. There's Barcel solution, Reiner-Nordström, the Kerr, and the Kerr-Newman solution. The first one is characterized by its mass, the second one by its mass and the electric charge, the third one by its mass and the angular momentum, and the fourth one is characterized by the mass, electric charge, and angular momentum. Obviously, before this research, some work has been done in this line, okay, trying to bypassing this the Norher theorem. For example, the first article trying to solve this issue were carried out by introducing, for example, a scalar field into the Einstein theory. In this way, the contribution coming from the scalar field can be interpreted as a new hair. Also, some people is including quantum effects, okay? But in this case, we shall try to bypass the theorem by using gravitational decoupling by minimal geometric deformation approach. It is worth mentioning that before this article, obviously, Professor Jorge Valle with his collaborator, they have done it some good research article in the same line. But today, the new things is that we are connecting this minimally deformed hairy black hole solution with wormhole space-time. So yesterday I talked about gravitational decoupling by MGD. Today I want to do a short revisiting regarding this methodology, okay? Recalling that for a perfect fluid matter distribution, okay, subject to a spherically symmetric and static space-time, if we put together all this information, this is the simplest situation, together with a new gravitational source, we obtain this complicated set of equations containing, okay, the usual thermodynamical variables and the usual metric potential along with this new gravitational source. In principle, we don't know anything about this gravitational source. This is completely new, but it is introducing new ingredients into the theory, okay? Then to solve this problem, as I said yesterday, we are going to decouple both vectors, okay? We want to split this complicated set of equation into two simple ones. And to do so, we introduce the so-called minimal geometric deformation transformation, where only one of the metric potential is altered, in this case, usually the radial one. And after plug this transformation into the box system, we obtain two separate systems. One of them, the usual Einstein field equation, okay? This system is already solved by the so-called seed space-time. And also we obtain this second system of equation containing four unknowns, the theta, mu components, and the decoupler function. So in summary, we can say that this protocol, okay, we can summarize this protocol following this simple step. First of all, pick up a solution of the Einstein field equation. It can be a perfect fluid, vacuum, anisotropic, charge, etc. Okay, as you feel. Okay, yesterday I was talking about a perfect fluid solution, and then after introduce the theta mu sector, we are translating, we are extending this isotropic solution to an anisotropic domain. But actually, it is not necessary to start from a perfect fluid solution, okay? You can start, as I say, from a vacuum, anisotropic, charge, etc. The main point here is to start from a known solution already solving Einstein field equation, okay? Then, to close the theta sector, we can impose some restriction, okay, on the theta components, or we can fix the form of the deformation function, or we can use the Mimi constraint approach, okay, in order to determine the decoupler function, and in this way, the theta sector. Then, after obtaining the decoupler function and the theta sector, we have the full characterization of the space-time, and finally, we have solved the problem in a consistent way. Then, the main purpose of this talk today is to apply this methodology to obtain Hairy black hole solution and connect them with Workhome SpaceTime. To do so, we will take the simplest space-time, okay, describing a black hole solution in the concept of general relativity. As you know, this space-time is given by this Barcel space-time, given by the line element 7. And this space-time has very nice feature. For example, this space-time, the temporal metric potential is equal to the inverse of the radial metric potential, okay? This is the so-called Kershil ansatz, where the function, the H function, has this form. As I said before, this solution has only one hair, okay? It mass, and it's subject to a vacuum energy momentum tensor, okay? A vanishing energy momentum tensor. Then we start from the Schwarzschild space-time, okay? This is the seed solution. This is our input. This is our starting point. This is the starting point, okay? This metric described by a vacuum energy momentum tensor. When we apply gravitational decoupling by means of minimal geometric deformation, we obtain a minimally deformed Schwarzschild solution plus new ingredients coming from the theta sector. And all these new ingredients can be interpreted as a new hairs. Then, in this case, we are bypassing the Nord-Hair theorem in a simple and consistent way by applying gravitational decoupling. Okay, yesterday I say we have at least 3 ways to close the theta sector, okay? An equation of state, imposing a suitable form of the deformation function, and using the Mimi constraint approach. Today, I'm going to apply the Mimi constraint approach. However, the original Mimi constraint approach proposed by Professor Jorge Valle and his colleagues is not working properly if you want to get new Hairy black hole solution by minimal geometric deformation approach, because this Mimi constraint leads to some drawback or trivial solution. Of course, this approach is working very well in the context of stellar interiors, but in this case, it's not working properly. So we proposed a new MIMI concept based on the total pressure of the seed space-time. Okay, the total pressure is given by this expression. Okay, as we know, in the Schwarzschild space-time, the energy momentum tensor is 0. Then this sector is 0, and it leads us to a differential equation for the decoupler function. Okay, when we relate both components of the theta sector, the radial component and the angular component. And we obtain this constraint when the total pressure of the theta sector, the equivalent total pressure, okay, of the theta sector is mimicking the behavior of the total pressure of the seed space-time. After solving equation 11, we obtain equation 12, okay? We determine the decoupler function. But at this point, something is happening because, as you can see, this function, the S function, is linear in the original metric component of the Schwarzschild space-time, okay? Then we have obtained a simple form for the S function. Of course, this result in general is not new at all, okay? Professor Jorge Valle have obtained some similar expression, okay? But as you can see, this is a very good property in some sense. I mean, the decoupler function is linear in the original metric potential. But here we have another element. We have an integration constant, okay, with units of length. And we have this expression here in the denominator. As you can see, immediately here we can detect a problem. If we evaluate this first term at r equal m, it is clear that this function is not well defined, okay? But then we need to investigate the new properties introduced by the gravitational decoupling by MGD into the system, okay? So in general, when you apply gravitational decoupling by MGD to the Schwarzschild space-time, the general form is given by 13. We are deforming just one metric potential, usually the radial one, keeping unaltered the temporal one, and this is the general form. But in this case, after applying gravitational decoupling, we obtain this space-time. This is the minimally deformed Schwarzschild black hole solution, okay? As you can see, we have the usual temporal component, and we have modified this component of the metric tensor. And here we have redefined the product between the alpha coupling and the integration constant as L, okay? This is a constant with units of length. And here we have our first result, okay? This L is a new primary hair. Then this black hole space-time, the black hole 14, has two primary hairs. The original one, the mass, and the new one, the constant L, okay? In principle, these hairs are not related. In principle, are not related. They are independent, okay, from each other. Okay, to establish a well-defined Workhome solution, first of all, we need to study the horizon structure. As we know, the original Schwarzschild solution has only one even horizon, okay? And this even horizon corresponds to the simple zeros of this equation. In this case, we have the even horizon at 2m, okay? When r is equal to 2m, we have the even horizon for the original Schwarzschild space-time. But for this space-time, this point is not only an even horizon. This is also, okay, a killing horizon. Okay, it has a dual interpretation. And also, we can see that 2m is not the only problematic point. at the level of this line element. We can see that if we evaluate this line element at r equals 0, we have an essential singularity, okay? We cannot remove this point. Of course, you know, we can remove this point, this problematic point. At the end, the geometric interpretation, the physical and geometric interpretation is that it is an even horizon, but this point is not. This point is an essential singularity, and taking into account the strong cosmic censorship conjure, this essential singularity should be protected by the even horizon. But when we apply gravitational decoupling, it is clear that from the minimally deformed metric potential, new critical points and simple zero are coming. In this way, we apply the definition, okay, to find out the even horizon, the potentially even horizon. We can see that we have 2 points, 2 simple zeros. The original one, and okay, we can expect that because, as I told you before, the decoupler function is linear in the original metric potential. Then it is clear that the original point is again a simple zero in principle. And also we have a new one, a new point, okay? And this point in principle could represent a new even horizon. Nevertheless, we need to take into account some things, okay? First of all, we need to have a well-defined horizon structure. But why do we need this? Because we need to preserve the causal structure of the resulting space-time. And why we need to do that? Why we need to preserve the causal structure of the resulting space-time? Because we can face some drawbacks if we don't do that. For example, the signature of the metric or of the space-time is not well defined, and also the expansion of outgoing geodesic vanish, okay? And ingoing geodesic never cross the even horizon, okay? At this point, the outgoing geodesic vanishes or in this limit, okay, when you are approaching to the wormhole from the outside, and ingoing geodesic never cross the even horizon. Then, to preserve the original causal structure for outer observers, we need to impose the following restriction. Restriction 19. This restriction means that the new critical point, the new simple zero, representing potential even horizon, should be inside the original even horizon, okay? We need to impose this restriction. In this way, we can avoid these two problems mainly. In doing so, for this specific case, for this particular solution, we can distinguish 3 cases, okay? We can distinguish 3 cases. The first one is when the parameter L, okay, is greater than minus M, but less than 0. It means that L is negative, is taking negative values. In this case, the minimally deformed Barcel solution acquire an inner horizon, okay? The so-called Cauchy horizon. From the mathematical and physical point of view, we know that these kind of surfaces are quite problematic, okay? Usually, if you want to study, for example, the causal structure inside the black hole, it is not possible to have a well-defined causal structure on this kind of surface. But in this case, this solution acquired a new horizon, the inner horizon. This is similar to the Reiner-Nostrom case. The second case, we can assume that L is a strictly positive quantity. And in this case, the new even horizon, R star H, has not a physical meaning because it takes negative values. And recalling that the radial coordinate in any black hole problem is positive defined, it is obvious that a negative radial coordinate has not sense. And in this case, our solution has only one even horizon coinciding with the original one. And the third case is when we take L equal to minus M. This means when we are taking the equality in this expression, when we are saturating this expression, okay? The saturation of this expression produce a degenerate even horizon. It means we are merging both even horizon, the original one with the new one. And the solution in this case, again, only has one even horizon given by 2m, the original one, the original value. And in this case, this is quite similar to the extremal Reiner-Nostrom case. So we can distinguish between three cases. But in all these cases, the new even horizon is hidden, okay? Is hidden or is protected or is behind the original one, okay? As you can see in this picture, here we have the black line correspond for when L is greater than 0 is positive. And in this case, we have just one even horizon, okay? The solution behaves as the original Schwarzschild one. But when we consider, for example, this solution, the cyan line, we have an inner horizon, the Cauchy horizon, and another one, okay, 2m. And if we consider, for example, the case when the new even horizon coincide with the original one, we have the magenta line, and this is similar to the extremal Reiner-Nostrom space-time. But in all cases, we are preserving the causal structure of other observers. Nevertheless, we have a new problem in some sense, because as you saw in our model, we have a new critical point, R equal M. When we replace this value, okay, in the solution, the inverse of the radial metric potential blows up. Then you can ask you, what is the role played by this point in the solution? Is representing, for example, this point another even horizon, or it is an essential singularity beside the original one? The answer is yes, it is a real singularity. Recalling that the original Schwarzschild space-time has a real singularity located at R equals 0. But when you apply gravitational decoupling by MGD, sometimes appear new essential or real singularity. And this critical point cannot be removed even if you are doing a change of coordinate, because this is the meaning of a real singularity. We cannot remove them, but we need to protect them by an even horizon, because, as you know, it is forbidden. Naked singularities are forbidden in nature. But then now, how is possible to classify this point as a real singularity? This is simple. Just we need to compute some invariance. An invariant is a quantity, okay, that remains the same. It does not depend of your coordinate, your system of coordinates. If we compute the Ricci scalar, of course, for the original Schwarzschild solution, the Ricci scalar is 0, but in this case, we have a non-trivial Ricci scalar. Unless you set L equals 0, obviously, you are recovering the usual Schwarzschild solution. And as you can see in expression 20, if you evaluate this expression at R equals 0, this invariant blows up. But also, if you are evaluating the same quantity at R equal M, then we have two real or essential singularities. But in this case, there is no problem at all, because both singularities are protected by the event horizon, R equal to M. But in this case, we have obtained a not globally defined black hole solution. Because when you are studying fundamental problems concerning black hole solution, the radial coordinate cover the range from 0 to infinite. But in this case, our model is not ranging from 0 to infinite. It covers just from M, the new real singularity, to infinite, okay? This point has not physical meaning here, okay? Independently, if you evaluate this quantity at 0, and you can say, okay, this is a real singularity because this scalar entity is ill-defined, but this is not the case. But we are not interested in studying fundamental problem. At this level, we are not studying fundamental problem in black holes, okay? That's why if our black hole solution is not globally defined, this is not a problem, okay? So, when we were doing this work, we say, okay, it is possible to connect this minimally deformed black hole solution with a wormhole space-time? Can we connect them in some way? Obviously, the answer was yes, we can do that. But first of all, before to present you this result, let me tell you some basic thing or notion about Workhome Solutions. As you know, Workhome are purely hypothetical solution to Einstein field equation. And not only to Einstein field equation, you can find out, you can solve, or you can solve this problem in any gravity theory beyond Einstein theory. But here we have the basic definition given by Morris and Thorne, and you can find it also in the well-known Weiser book. And it says, a wormhole space-time is an hypothetical solution consisting of a tunnel or throat connected to two identical regions. In the simplest case, the topology of the wormhole space-time is given by this, okay? By this expression, where R means the time, in this case, time coordinate. This R means the radius, and this is the throat, okay? And this topology corresponds to an static and spherically symmetric wormhole solution. Here you have a picture, okay? Here we are depicting schematically the form of a wormhole. But this is the, when I say this is the basic definition, because a wormhole space-time is just a throat connecting two identical regions. Sometimes people say that these two regions should be asymptotically flat, but this is not mandatory at all. That you need a tunnel or a throat connected to identically regions in order to have a completely geodesic space-time. Okay, the asymptotically flatness of this region is not mandatory at all. Okay, but those are the most commonly Workhome solution studies. Okay, and to build a Workhome, we need some essential ingredients. Okay, we need to do some engineering. Okay, here I listed some points, not all points, not all ingredients, just the most important ones. And the first one is to define the radius of the Workhome throat. We need to define the radius, okay, the region where the throat is located. We need a redshift function, okay, a finite everywhere redshift function. Also, we need a shape function satisfying the Workhome throat condition. We need to satisfy the so-called flare-out condition. And also we need to satisfy this condition, okay, in order to avoid change in sign of the metric component. We need to ensure that the radial metric component is always positive defined, because it is supposed that you can cross, okay, through the tunnel. This is the main difference between a wormhole and black hole solution. Once you cross the event horizon of the black hole solution, then there is no way to get out. But in the wormhole case, you can cross the wormhole. You can pass through the throat. This is the main point, that Wormhole Solution has not even horizons. Though taking into account these ingredients, in canonical coordinates, you can represent a wormhole solution by this light element, okay? As you can see, we have the redshift function. As I told you, this metric component, the temporal metric component, should be finite everywhere, okay? It cannot be null. Otherwise, if this function is vanishing at some point of the radial coordinate, we have, in this case, an infinite redshift surface. And then it should not be possible to crop the wormhole. That's why we need that this function should be different from 0 for every value of the radial coordinate. And here we have b. B is the shape function, okay? And when you evaluate this function at the Workhome throat, it turned out to be the Workhome throat size, and then you have here a problem in principle. But this is not a problem because we are using this canonical coordinate, and this canonical coordinate are not a good choice to describe many problems. The same like in Schwarzschild solution. When you evaluate the Schwarzschild solution at r equal to m, you know there are some problems, but then you can drop it out this problem by changing your coordinate system, your system of coordinates. Following this step and taking into account our solution, we have obtained this space-time, okay? Space-time 23 corresponds to the minimally deformed Barcel space-time, okay? If you compare this space-time with the most general line element, Alamori's thorn, okay, for a Workhome space-time, you can recognize that the redshift function is given by the original Schwarzschild metric potential, and the shape function is given by this expression. Okay, as you can see in the line element 23, at r equal to m, both metric potential are vanishing, okay? Okay, in this case, the inverse, not the original one. The inverse is vanishing, and GTT, or the temporal component, is also vanishing. But it is supposed that in the Workhome, in a Workhome space-time, this metric potential cannot be vanished, cannot be null. Okay, otherwise the Workhome space-time should not be a traversable Workhome space-time. So to cure this pathology, we relax this condition. Remember that this condition was imposed in order to preserve the outer causal structure, okay, of the space-time, but it was imposed in order to have a well-defined outer space-time, black hole outer space-time. But if you relax this condition, and if you allow to the new potential event horizon to be greater than the original event horizon, okay, if you, this is a simple inequality leading to this constraint, you can redefine the range of the radial coordinate to be this interval, okay? Now the radial coordinate start from r star to infinite, and in this way, the temporal component of this minimally deformed space-time is not vanishing. Is always, what is more, is always positive as required, okay? Then the temporal component has not associated any infinite redshift surface, and just the inverse of the radial component is being 0 at the Workhome throat as required. But we need to prove that. We need to prove that there exists a global minimum, okay, for the radial coordinate represented the Workhome location, the Workhome throat location. We need to prove that because, okay, we can redefine the radial coordinate range, but we need to assure that we can find out a global minimum describing the Workhome throughout location. And in fact, we are describing our Workhome SpaceTime. To do that, this is really simple. This is just, I can say, this calculus, essential calculus computation. Okay, this is not difficult. If we compute the first derivative of the radial coordinate with respect to the proper radial distance, okay, we can obtain the candidate critical point to be a global maxima or a global minimum. In this case, we have 2 points. We have the original even horizon of the Barcel SpaceTime, and also we have this second point. Now I have called it R1, but this is the same like R star H. And then if we evaluate the second derivative at this point, the conclusion is that only R1 or R star satisfies the above condition. I mean, this point is the global minimum. If you evaluate the second derivative at R equal to M, the second derivative is negative, okay? Then it is not representing a global minimum. It is representing a global maxima. But we need to prove that it is a global minimum. Then the point, okay, the point satisfying this condition is just R star or R1. As you can see in this picture, okay, this picture is representing the Workhome throughout location. Okay, we have plotted the radial coordinate versus the proper radial distance. As you can see, at this point, we have, is obvious that we have a global minimum, okay? And at this point, we have located the Workhome throughout. Of course, to do that, we have placed some numerical value for M and for L, okay? In our particular case, the Workhome throughout, the size of the Workhome throughout is 3 kilometers. But as you can see, the Workhome throughout coincides with a specific value of the proper radial distance, okay? This minimum is reached when L is equal to 0. And as we are connecting in this case, our Wormhole solution is connecting to asymptotically flat space-time. These 2 patches are covering by L when L goes to infinite. Okay, when L goes to minus infinite, then the radial coordinate goes to infinite. And when L goes to infinite, the radial coordinate goes to infinite. But when you approach to the Workhome throughout location, the proper radial coordinate tends to 0. Then we have demonstrated that it is possible to obtain a wormhole space-time starting from a minimally deformed black hole solution. On the other hand, it is quite interesting to study the so-called energy condition or the matter distribution treating the Workhome space-time. As we know, in the concept of general relativity, it was studied by Thorne and his collaborators. We know that in the context of general relativity, it is not possible to satisfy the energy conditions and the so-called flare-out condition at the same time. It is not possible. The flare-out condition tells us that the Workhome, okay, is expanding all time, okay? The throat remains open. We need the throat open in order to cross the Workhome space-time. But to obtain, to keep the throat open, there is no chance to have a normal or usual matter distribution. Usual or normal matter distribution is satisfying the so-called energy condition. Here in 29 and 30, we have 2 of them, the so-called weak energy condition. Okay, this energy condition is related with the preservation of the causality of the signal. As we know, there is no signal traveling faster than the speed of light. And the weak energy condition contain the null energy condition, but also have this restriction on the energy density. The energy density should be positive or 0 at least. These conditions are satisfied by normal matter distributions. But for wormhole solutions, if wormhole solutions are satisfying this condition, it means that the wormhole is supported by normal matter distribution, then the flare-out condition is not longer valid. And then it is possible, then in this case, the throat of the wormhole is not longer open. And this is the problem. Then if you want to cross the Workhome solution, the Workhome SpaceTime, you need to satisfy the flare-out condition, but we need to pay the price. And this price is the violation of the energy condition. Of course, in this case, it is not the exception. As you can see in this plot, our model is violating the energy condition. To satisfy the energy condition, you need to satisfy all of them, okay? For example, it is necessary to check the weak energy condition. As the weak energy condition contains the null energy condition, then if the weak energy condition is violated, it is obvious that the null energy condition is violated too. In our model, at least we have obtained a positive defined density. Sometimes this is also quite difficult in the concept of general relativity. Of course, you can tell me, okay, but this problem was solved introducing, for example, the extended gravitational theory or some modified gravity theory like FR gravity, FRT gravity, etc. Yes, I know that. But the problem is that in all this theory, also you need to pay some price. Okay, it is not free. You cannot satisfy the energy condition and the flare-out at the same time. We need to pay some price. Okay. In the concept of general relativity, I repeat again, we are violating the energy condition. Here we are applying gravitational decoupling by MGD. Of course, we are beyond, in some sense, we are beyond Einstein gravity, but it is not possible, okay? It is not possible too, as in the pure GR framework. But at least we have obtained, as I told you, a positive defined energy density. It is really good. Actually, it is really good, okay? We are satisfying the energy condition along the transverse direction. Nevertheless, along the radial direction, it is violated. It is taking negative value. And it happened because the radial pressure is greater than the density. I'm talking about in magnitude. If you take the absolute value, okay, the radial pressure is greater than the density, and obviously it's taking negative value. That's why we are violating this one. But this is not the problem at all, because as I told you, this is common in the concept of general relativity. But at least we have obtained this one. I want to highlight this behavior for the positive density, okay? Then this Workhome solution is treated by exotic matter, okay? Matter distribution violating the energy condition are called exotic matter distribution. But one question arises, okay? What kind of exotic matter supports our model? Because when you say exotic matter, what is the meaning of exotic matter? Okay, the meaning is they are violating the energy condition, but what kind of exotic matter exists? Okay, we have, for example, in the cosmological constant, for example, we have quintessence fields, for example, phantom fields, or the cosmological constant regime. This is the equivalent to the dark energy, okay? And to further investigate what kind of exotic matter is supporting our model, we need to investigate, we need to obtain the equation of state. And here, in this expression, okay, you can see the thermodynamical variables of our model, remembering that we start from an empty space-time, then there is not contribution to the seed of the seed space-time to this expression. Just this expression contains only the theta mini information, even in this expression. If we compute the equation of state, if we compute the relation mainly the relation between the radial pressure and density. Okay, if we obtain the so-called Tropic Equation of state, we have this expression, expression 34. As you can see, this expression is a barotropic equation of state, but this is a non-linear barotropic equation of state. When I say barotropic equation of state, this is a relation between the radial pressure and density, but this is linear in the density, okay? But here it is obvious, this is not linear. But if you expand this expression around the Workhome throat, keeping the lower order in row, we found this expression, expression 35. And as you can see, keeping just the lower order, we can see that at the Workhome throat, the matter behaves satisfying a linear equation of state, okay? A linear equation of state, a usual barotropic equation of state. With this information, we can determine what kind of matter is supporting our Workhome SpaceTime. As you can see in this plot, okay, in the upper one, we have the equation of state, and this, the black line and the magenta line is representing the linear approximation. Here it is located, here we have plotted the PR, okay, the radial pressure against the density. And this region corresponds to the Workhome throat. As you can see, it is linear, okay? It is satisfying a linear equation of state in this linear approximation. But if you plot the behavior, if you investigate what the equation of state parameter behaves, you can see this picture. Here we have the light yellow region correspond to the phantom region. This dashed blue line correspond to the dark energy, okay, or cosmological constant. And the light blue region correspond to the quintessence fields. But as can you see, the equation of state parameter is living on the phantom field regime. Then our Workhome solution is being supported by a phantom field, an exotic matter distribution that concretely a phantom field. Furthermore, this equation of state is non-linear. Consequently, we have a non-constant or a varying equation of state parameter, okay? Usually, when you impose an equation of state, the equation of state parameter is constant, but in this case, it's not constant. So now we can conclude this talk, and obviously there are some open questions, okay, regarding the study of hairy black hole using gravitational decoupling by minimal geometric deformation approach. But first of all, some conclusions. Using gravitational decoupling by minimal geometric deformation, we obtain an asymptotically flat, non-globally defined hairy black hole solution characterized by two primary hairs, the mass and the parameter L. I say primary hair because in principle, this parameter are not related. But in the case when you merge both even horizon, then L is not longer a primary hair. Now it's a secondary hair because it depends, its magnitude depends on the magnitude of M. Also, I want to highlight this property, asymptotically flat. Why? Because if you apply MGD, maybe you can lose this property. The original spacetime is asymptotically flat. If you take the limit when you are tend to infinite, you are recovering the Minkowski spacetime. And here we are preserving the same property, okay? Secondly, the non-globally defined character of the black hole model is a consequence of the new real singularity, okay? Now we have this new real singularity. It means that the range for the radial coordinate is not longer from 0 to infinite, now is from M to infinite. The third conclusion is the causal structure of our observer is preserved by MGD approach after some condition. Obviously, if you are not imposing the mentioned restriction where the new potential event horizon are hidden by the original event horizon, then it is not possible to preserve this condition of the spacetime. Then, taking into account the new critical point obtained from the minimally deformed Barcel spacetime, it is possible to obtain a Workhome spacetime. This is one of the main results. You can connect a minimally deformed black hole solution with a Workhome spacetime. And obviously, the matter distribution treating the Workhome spacetime correspond to a phantom field. Okay, this is the kind of exotic matter distribution that our model has. And as an open question, I selected this one. One question is, it is possible to obtain a globally defined black hole solution using gravitational decoupling by MGD? At first glance, who knows? I mean, at first glance, as you can see, MGD is introducing a new primary hair, okay? Really good. You can impose some restriction to preserve the causal structure, good. You can preserve the asymptotically flat behavior of the output, very good. But if you want to study a more fundamental problem in the black hole arena, you need to get a globally defined. Then the question is, this is an open question. It is possible or not? Under what condition it is possible to do that? What is the form of the decoupler function? What kind of matter is treating this space-time? If so, is the solution asymptotically flat? Sometimes when we are trying to fix some feature or to keep some feature, there are some drawbacks. I mean, you are enhancing some property, but then another property is falling. And then that's why I put this as an open question. Then it is possible to get a minimally deformed black hole satisfying the energy condition. Maybe this is not a mandatory requirement, but it should be good because in my case, the energy conditions are violated. Okay? But it is supposed that the black hole solution in some sense a real object. In the Workhome content, it doesn't matter. Okay? But in the black hole content, it is important. But here we can justify it by saying, okay, we are beyond Einstein gravity. And maybe beyond Einstein gravity, when you are including new ingredients, it is not possible to keep this property regarding the behavior of the matter distribution. And lastly, under what condition does the original event horizon not become an essential singularity? I did not discuss this point along my talk, but just I want to mention it here because sometimes the original event horizon, for example, if you are working, if you are starting from the Barcel spacetime, okay, it depends regarding your seed spacetime, okay? But in this particular case, sometimes the original event horizon become a real singularity. Then we have a major problem because in the original problem, we know that in this Barcel solution, R equal to M is an even horizon. It is not an essential singularity, but sometimes it happens. But then the question is, under what condition does the original even horizon not become an essential singularity? Okay. Thank you very much for your attention.